Hi everyone. Thank you so much for coming to my talk. I'm going to talk about partition statistics in Iceberg. And myself, I am Ajantha Bhat. I work at senior software engineer at Dremio. I mainly contribute to Apache Iceberg, Apache Polaris, and Project NSC. And I flew all the way from India to give this talk and to meet some of you guys. Good to see you all. So the agenda of the talk is, first we're going to see something about, overview about a cost-based optimizer because the statistics are used with a cost-based optimizer. And we're going to see types of statistics available in Apache Iceberg. Then we're going to see use cases, where and all it is used, who is looking forward to use this feature, and the partition statistics spec, which is present in Iceberg already, and how the engines can use this API and implementation, and what is in the future roadmap for this feature. So we'll start with an overview of cost-based optimizer. As we all know, most of the query engines, if we run a query, it is going to be converted into a logical plan, and then it will be executed with a list of operators. So the cost of each operator is either an I/O cost or it's a CPU cost and the network cost. So if you see a estimator, so here, as you can see, it takes the plan, and the estimator will get the statistics to figure out selectivity. Selectivity is how many output rows out of the total rows it is going to get, and the cardinality, whether it's a low cardinality, high cardinality. So based on that, it is going to estimate a cost. The cost-based optimizer will have a choice. So out of multiple plan, it is going to choose the best plan, which is with the lowest cost. So that plan going to make your query run as fast as possible. So if you consider a scenario where a data scientists want to know which customers spend most of the dollars, they're going to run a query something similar to this. It's a TPC-H, most of us are familiar with it. So we have a customer table, order table, and line item table. Here, the customer table is 1.3 million rows, and the orders is 15 million rows, and the line item is 61 million rows for a 1 TB of the data. So as we know, most of the engines, where if we have to join this particular table, so if we have to run this query, we have to join it. And the join ordering is one of the major factor for a optimizer to take a decision, because the join, we are going to broadcast some of the tables, so it is going to be in memory. So the smaller table, we have to keep it in the memory. To know whether a table is small or big, we have to know about statistics, how much rows it is going to have. So statistics going to help in deciding the join reordering. If, for example, here, if we keep the customer and the order, if we just change the join with the orders to customer, keeping the customer on the right, it's going to make your query run very, very fast. So if you can consider other case, now the customer want to know who repeatedly bought and spend most money on a particular item. For example, on which smartphone they spend most money on. For this, we are going to add a filter condition to this, to what was the previous query. Here, if you can see the line item, I want to know which item has more. So with this, here now we have to know for this particular filter what's going to be the output rows. So again, we have to depend on the statistics to know how much output rows going to come with this particular value. Most of the time, the table will be partitioned in the real world. So the item, whatever the filter condition is applied, they're going to be a partition, and we might have to know what's the output rows for that particular partition. So here, as you can see, the similar query, we are going to move the filter condition to the line item, and the line item will be moved on the right, so that it will return smaller number of rows, so it is easy to keep in memory. So, and first we are going to see what are the types of statistics available in Apache Iceberg. As we are all familiar with the Iceberg spec, the Iceberg has a manifest file where it has entries for each data file. So each data file has a record count. So, and then for each file level, it knows how many record it has and what is the file size in the bytes. And each file, it has a column level statistics. Like for my each column, what's the column size, what is the value count, what is the null value, is there a non value, then the upper bound and the lower bound. And it also represent what partition it is going to belong to. And then we have a manifest level statistics in the manifest entry. So in the manifest list file, I know for each operation that's going to happen, how many added files, what are the existing files, how many deleted files, added rows count. We have the files count and a rows count. Along with that, we have a partition field summary, because a single manifest list can map to multiple partitions. So for each particular partition, it knows what is the upper bound and the lower bound of the partition range for that particular insert. And then we also have a snapshot summary, which is that table metadata file is having a snapshot, and snapshot's going to have for all the entire operation, what is the added data file, added delete file, and the total data file, all those things. And we also have an optional partition level metrics with the same what were mentioned here. And then we also have a table level NDV, which was recently introduced as a Puffin file. Instead of storing it as a Apache, Iceberg stores it as a Puffin file. It's an Iceberg proprietary format, because we just want to store the blobs. Storing them in a Apache is not efficient, so we have our own format. It's a magic blob and with a footer. And this NDV is a non-distinct value, so if you want to know how many unique values exist for that particular column at a table level, we just have to open this particular Puffin file, and you can see more about the Puffin spec here. But until recently, we didn't have anything at the partition level. In the real world, most of the tables are partitioned, and the queries will always run on that particular partition filter. So we come up with a feature called partition statistics, and we propose it in the Iceberg. So I'm going to dive into more of the use cases. So one of the first initial use case, we want to avoid reading all the manifest file for each query. For example, I'm doing the query, I want to know what and all partitions is there. I have to go through millions of the manifest file, which is not efficient. Yesterday, I was talking with the Pinterest, and they mentioned that they have a use case. Like, for example, they want to list all the partitions of a table within 10 seconds in their UI. As of now, we don't have anything for this in the Iceberg spec, so they have to read all the manifest. If you have the partition statistics file, they can just read one single file. You can get it in the sub-seconds. And the second use case is to estimate the parallelism. Parallelism, for example, if you are building a query engine, which is going to auto-scale, so at the query planning time, we want to know whether this query, how much resource it requires, how many nodes I need to allocate. So for that, I need to know the statistics. So for that, for this particular query on the partition filter, so we have to know this parallelism. It is going to help in query planning. And we also discussed previously, it is going to help in the join reordering. Similarly, there are going to be IO operator selection for a query planner. For example, whether I need to run a distributed IO or a local IO. It is based on the number of rows I'm going to get out of that partition filter. And also, this is one of the important, the partition statistics can help to know whether do I need to run a compaction on that particular partition or not, whether that is last modified or not. So I can get that info just by looking at the partition statistics. And also, yesterday I was talking with the 2 Sigma, and they mentioned that now they cannot expire a snapshot in there. It is because they want to know the last modified snapshot time for that particular partition. And if that partition has changed, they want to run the job for the affected pipelines. So because they cannot expire the snapshot, their table metadata file is bloated up, and it is impacting them each and every query. So if they have a partition statistics file, they can expire the snapshot, because that last modified time will be tracked on that partition statistics. And also, we have Hive and Trino engines waiting for this particular feature. The Hive has recently integrated the partition statistics. They're using it for some of the optimization. Like if some of the users want to run count star query on a partition value, so without reading any of the manifest, they're going to get what's the count of the records in the partition using this. And they also have PCR optimization, which they're going to use it. And the Trino want to enhance the current Iceberg spec. They want to have some more column level statistics for per addition. I'm going to dive more into that later. So let's go through the spec which is present in the Iceberg. So in the Iceberg table metadata, we track the partition stats using a field called partition statistics, and it has a snapshot ID for which this particular stats are written, and the path, which is a partition stats file path, and the file size in bytes. As you can see on the right side, the table metadata JSON gonna track. It looks something like this if you open a table metadata. So because it is tracked by the table metadata, if you run an expire snapshot, whenever that snapshot is expired, it is gonna clean up the old partition statistics files, and remove orphan files is not gonna clean up this particular file because it is tracked by the table metadata. And if you see what is this statistics file, how it is stored. So as of now, Iceberg supports storing this in a table default format. For example, if you write the statistics, if you write your table in Avro, you can write the partition stats as Avro. If you write it in a Parquet, you can store it as a Parquet, like that. So the schema of the file will look like this. The partition tuple will be maintained. So for each particular partition, what is the spec ID, what is the data record count, file count, and the total size in the bytes. And we also have the delete record count, position delete file count, equality delete record count, equality delete file count, and the total record count. If you don't want to apply the delete count manually, if you want to get the effective count, you can use the total record count if your engine can support computing it. And lastly, we also have last updated it. For example, that particular partition, when was it last modified, and which snapshot was last modified this particular partition. And the partition stats file name look like this: partition stats, snapshot ID, UUID, and the format extension, like that. So the next thing we can see how the engine can integrate it and what APIs are present for it. So we have in Iceberg core and the data API module. It's a simple API. We have a utility called partition stats handler. Here you can call compute and write stats. You can just pass a table. It can compute for the latest snapshot, or if you pass some snapshot ID, it can compute for the particular branch of the Iceberg. So, and we also did some POC, whether for this compute write stats, whether to use a local algorithm or to use a distributed algorithm, because it's always exciting to make things distributed as we are in a big data world. But what we observed is that the serialization cost is too much if you are going with a distributed algorithm. We can read all the manifest in parallel with the distributive, but once you compute the stats and once you send it back, that cost is very, very high as compared to computing it in a local threaded algorithm. We also checked a large number of files, like a 10,000 partition per, having 2 data files per partition value, and we also checked like a 20 partition having 10,000 data file value. With both this scenario, we came to know that the local algorithm performs better. So this, whatever the API compute and write stats file, is going to use a local algorithm in a multi-threaded way. And once you have that particular partition stats file which is written, you need to register it to the table, like as we have done here. We have an API expose test table.update partition stats, and we can just pass that and commit. We can also, this partition statistics is also supported by the REST catalog, so we have endpoints to commit and fetch these statistics. Also, lastly, we have a Spark procedure. So the people don't want to use the APIs I mentioned previously. They want in a equal way to compute the stat as easy as possible. So you can just do call this and you can pass it, and you can fetch the statistics using table.partition stats file. So feature roadmap. So we are also working on an incremental compute of this partition stats, because we don't want to compute all the stats again by reading all the manifests. So if if there is a partition stats exist for some snapshot, from that snapshot to the current snapshot, whatever the gap is there, we are going to read it and we are going to incrementally compute that stats. And that incremental stats is going to be written back into the storage. So we have a PR up already. It's going to be released with Iceberg 190, which is coming up. And we also want to support delete vectors. As we mentioned in the V3 spec, we are coming up with a delete vector. So along with the equality delete and the position delete count, we also want to include the delete vector counts here. And we want to integrate the partition stats with other engines like Trino and Hive. Hive 4 has already integrated it. They have to release it. Trino is excited for it. So the Trino and other people have, now as you see in the spec, whatever the schema of the partition statistics file, which is mentioned previously, it is not having a column level statistics. It is only added file size, all those things. So we still need a column level statistics at a partition level. Also, we might need an NDV value, what we discussed with the Puffin files at each partition level to take a better decision for the partition pruning, etc. So we are also working on these two proposals where we are going to bring the each partition level, my column, what is the min, max, and upper bound, lower bound, and what is the null count, all those things. So yeah, these are the things which we are excited to, and we are working on in the future roadmap. Lastly, and I work at Dremio. This particular feature was initially developed at Dremio. It was already integrated with the Dremio, and then we wanted to give it back to the community after seeing how much useful it was for us. And so Dremio is an intelligent data lake platform, and it accelerates AI and analytics with autonomous performance, unified data, and AI-ready data products. So we are also early adopters of Apache Iceberg from the inception days. We are original co-creators of Apache Polaris, Apache Arrow, and Dremio is the only lakehouse that built natively an Apache Iceberg, Apache Polaris, and Apache Arrow. So we provide a flexibility, we prevent lock-in, and enabling the community-driven innovation. And we are also one of the fastest query engine available for Apache Iceberg because we support reflections. It's like a materialized views and such. So feel free to visit our booth. It is a booth number 1 down there. And we also announced our newest release in the morning today. It has autonomous reflection, and it also supports enterprise level catalog powered by Apache Polaris. And we also support Iceberg clustering. We are one of the early engines to support the Iceberg, early enterprise engine to support the Iceberg clustering. You can sort the data when you do the writing. And we also enable AI-enabled semantic search. So yeah, feel free to visit our booth and talk with our guys. Yeah, it's a short talk. That's it. I didn't want to go into too depth. So I think it was enough to get an idea how things work. If you have any doubts, any questions, feel free to contact me. Yeah, thank you.
Okay, thank you very much, Ajantha, for this great talk. We still have time for questions, so are there any questions? We have one here.
Thank you. So my question is, we have some production table, so especially bucket by 10,000 buckets. So I did some quick math, so the partition count can easily goes up to 100 million. Is there any performance concern about the current implementation?
No, we have also done a benchmarking, like we have tested for 200 million partition. We can do the read and write within minutes. We can do the write in the minutes, and we can do the read in the sub-second. So we don't see any content. The current because it's a columnar format, we are storing it in a Parquet. You can just fetch the partition record just by reading a column, not reading an entire file. So also the incremental update is something which is required for you. Without that, you can't read all the partition stat. So I don't see any bottleneck for that. So feel free to use it. And
okay, thank you.
I
have a follow-up question.
Sure.
So for the integration with engine, so you mentioned that the core part is done. Our workload mostly happens in Spark, so I'm wondering like what will take to integrate this into Spark?
Yeah, we have an open PR for that Spark call procedure, but the Spark cost-based optimizer don't have the partition level stats tracking. So we are thinking to propose with the Spark community and discuss with them how their interest to use this partition level stats on it. They only have a table level statistics in there. Whatever the Spark exposes some of the interfaces for cost-based optimizer. So we need a new interface at the Spark level to do this.
Okay, thank you.
Thank you.
More questions here?
Sorry, I missed the slide earlier. So I was wondering, with partition stats, how much improvement we are seeing?
It depends on the engine. Yeah, it depends on the query planner. Like some of the engines might have a lot of operators. Like they have to choose from lot of plans. So in those engines, we can see a drastic improvement. For example, if they want to do a broadcast join instead of the hash join, all those things, there, if they choose a better planning with respect to, we had a internal benchmark at Dremio. We didn't want to put the benchmark because nowadays benchmarking is just a benchmarking. So instead of that, we want the users to run the benchmarks and let us know. It depends on you. So if the partition stats can help to choose the best plan for your engine. So as long as that plan is fastest, and so your engine can run fastest with the partition stats. That's what I can say. Instead of comparing, there are chances that your engine choose the wrong plan and the query is gonna take hours instead of seconds. It can even sometimes you can see that queries can finish in seconds because it chose the right plan.
Okay. So can I summarize it? It's because this feature helped the planning
Yes.
and also overall SQL execution.
Yes.
Like scan how many files.
Yes.
Okay. Got it.
Thanks.
So I think you mentioned that there are two levels of partition statistics, one on the manifest level, one manifest list level. So why you ended up with two levels of statistics? Isn't it?
No, it is initially, like for example, the one which is at the file level is, it tracks about a column level statistics per partition. It knows that for my partition value, what's this? And here, the single manifest list can have a range of partition. So now we can have a lot of manifest list file, right? For each operation, it is going to create one manifest list. So we are going to have a lot of other, and we don't have those aggregated statistics here. So we need a separate file without reading any of this file to get the aggregated partition statistics.
Okay, thanks. Any more questions? Here's one.
Hi, I have a question about the column statistics, about timelines. Like, so do you have an idea when column statistics would be available in the partition spec files?
In a 3 to 4 months, yeah. Now, there is a proposal from the Hive community to add a column level statistics. So we are going to discuss in Iceberg sync, upcoming sync, and we are going to have it very soon.
Okay, but I think the metadata format, the Parquet table with the statistics,
This one?
didn't really have anything about columns, so it
Yes.
would need to be a spec of it.
Yes, we need to update the spec, but we don't have to introduce a new version of the spec because we can make them as an optional field. So with a current spec, we can have those. So yeah, discussion is about updating the spec first, and the implementation not going to take much time.
In general, for joins, what is the recommendations? Should the smaller tables should be on the right-hand side?
Yeah.
On the first slide that you pointed?
It all depends on the engine, so we cannot have a specific rule. So the engine, whatever it is going to broadcast, whatever table it is going to keep in memory, it has to store a smaller. For example, if you consider a Spark, you have to have the smaller table on the right.
On the right-hand
So if you consider some other engine, Dremio, it may be different implementation, and other engine may be different implementation. So it's based on that.
Okay, any more questions? One more here.
What about integration with Flink?
Oh, the Flink integration is still open, and the Iceberg community was not fully working with the Flink till now. That the activity was less. Now the Peter and other people have started working on it. So it is based on the interest. The innovation moves that side. So yeah, I think if anybody is willing to contribute it, they can start adding it as of now with 1.90 release. If not, I will add it soon after maybe 1 or 2 releases.
I see. And then for the Spark one, do you envision that will be a relatively long process, at least 6 months?
Yeah, Spark will take a time because
Okay.
they need to use it. The Spark engine level, they don't have a partition. And it's going to bring a lot of value to the Spark as well.
I see. Okay, thank you.
One more.
So, very interesting still numbers.
Yeah.
Top of your head, what's the best improvement with this feature? If you've seen Spark or Dremio.
Yeah,
Best record.
yeah, we saw some of the queries which are like we cannot compare with other engines. We just have this with a Dremio. We had some of the queries which took around like 2 minutes or something, which can now complete within 10 seconds. So, but not all the queries, because if you have only the choice of multiple operators, there you can do the better. And we also saw some of the optimization not useful for some of the engines who don't have cost-based optimizer, who has a rule-based. For them, the queries are always same because they don't use these statistics at all.
For the V3 specs, are you going to also store like the column levels information on the partition spec?
Can you repeat that?
It is for the recording we need.
So for the V3 feature of
Yeah.
Iceberg, which would have variant, right?
Yeah.
Would you also store those items at the partition spec?
Yes.
Is there any plans?
Yes,
for
yes,
that?
same. For whatever the data type for each column we are going to store, it will be stored at a column level. So for the variant also, we will be supporting the min-max, upper bound, lower bound. So same thing gonna translate if we make it as a partition column. Yeah.
Okay, then I think we can conclude the session here.
Yeah.
Thank you very much, Ajantha, for this great talk.
Thank you so much for coming. Yeah, you can visit our booth and you can reach me. I will be here till the evening.
Perfect. And
Okay,
then
thank you.